In the previous lecture, we talked about the fluidized beds. We talked about fluidization. What do we mean by fluidization? The types of fluidization and where fluidization is applied. And this lecture, I'm going to introduce three important concepts. One about the relation between bed height and porosity, and the other one is between pressure drop and the minimum fluidization height of the bed, and something called sphericity or shape factor. So three main concepts that are important that I'm going to talk about. So let me start with the first concept. So let us go through this slide, and let me go through the text here. So the relation between the bed height L and the porosity epsilon, طبعا height or length, here we are using the same thing here, and the porosity epsilon, porosity is the void fraction, if you remember from the back bed, is as follows. So for a bed having a uniform cross-sectional area A, so suppose I have, this is the initial state where I have a fixed bed, and suppose I want to know what is the volume of the particle. So those are the particles here, and let us say this is, instead of, now it is called Lm, let me call it for example L1. So I know the length, and then I know also the area of the bed. Let me call this A. And I can call it A1, but A1 is equal to A2, since those are, this is the same bed, equal to A. Okay, so now suppose I ask you, what is the volume of the particles inside this bed? You will tell me that, for example, suppose this is V1 and this is V2. So I put the particles here and I ask you about the volume. He will tell me V1, the volume of the particles here, equals to A1 times, you will say L1. Okay, but please notice I'm talking about the particles. So this is the volume of the bed. This is the volume of the bed. And since I'm talking about the particles, so I have to multiply this by 1 minus epsilon 1. Why? Because if you remember, this is the ratio of the particles in the bed divided by the total volume. So this is the total, this is like the total volume. This is the volume of particle divided by the total volume. So I'm going to get the volume of the particles. I want the volume of the particles. So actually then I can say that the volume of the particles is equal to A1 L1 1 minus epsilon 1. This is the volume of the particles in this case. Then suppose now I increase the gas velocity. Okay, I increase the gas velocity, as you can see in the second case. But the volume of the particles didn't change, it just expanded. As you can see, I didn't add any particles, I just increased the velocity. So the particles, now the length has expanded to this length. So if this was L1, then this is L2. A1 is still equal to A2. So then I can write, for example, if you want, V2 is equal to A2 L2 times 1 minus epsilon 2. Because now the porosity in this case is more than the porosity in the first case. So this is, again, this is equal to that. But as I said, I didn't change the area of the packed or the fluidized bed. And also I didn't change the volume of the particles. So I know that V1 is equal to V2. And I know that A1 is equal to A2. So this will give me the relation, this relation. So this will give me the following, what? A1 or A, just A, L1, 1 minus epsilon 1 equals A, L2, 1 minus epsilon 2. And this is what you see, in this equation. Okay, so this equation comes from, let us call it volume balance. I have two conditions. I can have, for example, this is the first condition and this is the second condition. So this can be, for example, the backed bed, fixed bed, and this can be at the, I can call it the minimum fluidization. So whenever this bed is, let us say, is expanded. So I can then have a relation. I can rearrange this equation into that. So I will just take L2 here. I will take this A the other side. Actually, the A will cancel with the A because A is the same. I didn't change the areas. And finally, I have this relation between the ratio of length of the bed, let us say when it was fixed and when it was fluidized, and to the porosity when it was fluidized and when it was, let us say, packed. So let me just go and read this statement with you. So the relation between the bed height L and the porosity epsilon is as follows for a bed having a uniform cross-sectional area A. Since the volume LA 1 minus epsilon is equal to the total volume of the solid if they existed as one piece, as you can see. So I have the solids, I didn't change them, I didn't take from them, I didn't add to them. So where L1 is the height of the bed with porosity epsilon 1 and L2 is the height with porosity epsilon 2. So this is the first equation, and you know how it was derived. It was derived based on the volume balance. Now let me go to the second concept, and here I want to get a relation between the pressure drop and the minimum fluidization velocity. So again, I can look at, for example, these two conditions, but the main thing is here, is this, let us say, force balance. So whenever I have this, let us say this case where I have the fluidization condition, those particles will be hanging. They will be in free fall. They are not going to be attached to each other. So they will be like flying. So there is nothing, I mean, the forces are equivalent on each particle. So I can go and look at the force balance. So let me read this statement. So at the start of the fluidization, the force obtained from the pressure drop times the cross-sectional area must equal to the gravitational force exerted by the mass of the particle minus the buoyant force of the displaced fluid. So what do we want to do now is to do a force balance. So once I am in this state, as I said, the particles will be hanging there and the forces on them will be balanced. What are the forces? We have three forces. We have, let us call it the weight force, if you want to call it, which is the weight of the particle. I can have the buoyancy force and I can have the drag force. So FW, FB, and FD. So FW, طبعا, it is the weight of the particle. So once I have this particle just staying where it is, the forces are balanced, then I can equate those forces. But let us first look at these forces and write them. So F, let us call it, I don't know if shall I call it FW or let us call it FG. So FG is the gravity force, is equal to what? It is equal to the mass of the particle multiplied by G, or the mass of the particle multiplied by G. And you know that the mass is equal to the density of the particles times the volume of the particles, if I'm looking at the whole thing. And this is طبعا multiplied again by G. So this is MP, M of the particles, equal to the density of the particles times the volume of the particles. But I have just showed you what is the volume of the particles in the previous slide. So this is equal to the density of the particles. What is the volume of the particles? Is equal to the length of the bed times the area of the bed times 1 minus, let us say, epsilon, let us call it epsilon 1, or I can call it epsilon minimum fluidization. Okay, since I'm talking about the fluidization condition. And طبعا I have to write the G here. So this is the gravity force. Then this is the gravity force on the particle. As you can see, gravity force equal mass times acceleration. Mass is equal to density times volume times G. And this is the density, this is the volume that I showed you in the previous slide, and this is G. So this is the gravity force. What is the buoyancy force? طبعا, you know from chapter 1, the buoyancy force is the force, let us say, it's equal to the weight that is displaced by the fluid. So now it is the same thing. So I have just write MF here, which is the mass of the fluid times G. is equal to the density. طبعا now it is the density of the fluid, everything else the same, so V of the particles, because this is the volume which was, let us say, displaced, times G, and this is equal to the density of the fluid, and now it is the same thing here, so L1, طبعا I can write it L1 or I can write it LMF. It should be LMF since I'm talking about minimum fluidization length. Okay, so this is, again, this is A1, or I can call it just A. Okay, I can erase this this one so not to confuse you. Let me go back to this. So, and this is now equal again to 1 minus epsilon minimum fluidization, and this is G. So this is the buoyancy force. The buoyancy force is the same as, let us say, the gravity force, but it is applied on the fluid. So this is why I replace the main differences. I replace the density of the particles with the density of the fluid. The last thing is the drag force. So I'm done with this. I'm done with that. So now what is the drag force? The drag force is equal to the delta P times A. So FD is equal to delta P times A. Okay. طبعا in this condition you can see that, I mean, once I have the balance, once they are equal, I can write what? I can write the following. I can write that Fg, the weight force, is equal to Fb plus Fd. Okay, Fd plus Fb is equal to Fg, and you can just substitute those values. I mean, I can substitute this Fg here, Fg you can substitute it here, Fb you can substitute here, and Fd here, and you can solve for the relation between delta P and LMF. Let me go to the next slide. So once you do this, once you just substitute for the values, you will get this equation. Delta PA is equal to the length at minimum fluidization times area 1 minus epsilon minimum fluidization, the density of the particles minus the density of the fluid times G. And if you rearrange this equation, طبعا from where we got this equation, again, from where we got it from the substitution the previous slide. So Fg is equal to Fd plus Fb. Just do the substitution, you will get this equation. طبعا I can take this LMF to this side. I can cancel the A's and take LMF this side, and I'm going to get this equation, which is a relation between, let us say, the pressure drop per unit length of the bed, and it is equal to this equation here on the right hand side. If I want it in the English system of unit, then I have to watch for the conversion, which is using the GC when I want to go from SI to the English system. So this is the second equation, and we derived it from the force balance. So this is the force balance, and the first equation was derived from, let us say, the volume balance. So this is the second concept. Now the third concept is called sphericity or shape factor. Sphericity or shape factor. What is it, and why do we need it? So usually in fluidized beds we will have non-spherical particles, and we talked about this before. So for non-spherical particles, instead of the diameter, an effective diameter is defined. And you remember we said this before when we defined the effective diameter. Now sphericity or shape factor is defined as the surface volume ratio for a sphere, which is this is the sphericity or shape factor. It is equal to the surface volume ratio for a sphere of diameter dp, which is this, divided by the surface volume ratio of a particle whose nominal size is dB, which is this. Okay, and this is, I mean, the diameter of the particle, we call it nominal size, or we call it equivalent. We call it nominal diameter, or we call it equivalent diameter. So as you know, for a sphere, SP by VB is equal to this, and I will keep it for the particle as that, SP by VB, and you know that this is equal to A sub nu. Okay, so by letter rearrangement on the next slide, you can see now A sub nu, which is this, and you don't have to worry about this detail because I already talked about it. So from here you can see that I can get this relation. So A sub nu is equal to 6 divided by phi s, which is sphericity, times equivalent or nominal diameter. And what is the difference between this equation and the other one? I mean, in the past, there wasn't this phi s. This dp is not the it is not the old one, which is the diameter that we defined before. Now this is called nominal or equivalent. How we get it? We get it from sieve analysis. This is called sieve analysis. So we put the particles inside this sieve, نفس المشخالة, and then I know the particle, or let us say the whole size, and this is called the equivalent or nominal size to be substituted here. Okay, to be substituted here. And then in order to correct for the diameter, I will use the shape factor. And so this is for A sub nu. And what about for A? For A, again, I am just putting dp times phi s. So all in all, to make things here simple for you, the only difference that I have to make once I have the shape factor or the sphericity is just to multiply. So I replace, so in the past, I have dp. In the past, we have dp, which was called effective diameter. But now suppose I don't have the effective diameter, I have the nominal or the equivalent, so I can use the sphericity shape factor. So if I multiply phi s, which is sphericity or shape factor, times the equivalent or times the nominal, this will give me the other one, which is the effective diameter. So all that I'm going to do is just to replace the effective with phi s times nominal or phi s times equivalent. So for cylinders whose diameter is equal to, so suppose I have a cylinder whose diameter is equal to the length, then this is the sphericity. So there are tables with the sphericity or shape factors, so it will be given to you. For a cube, so if I have a cube, then this is the sphericity or shape factor, and usually typical values for many crushed materials are between 0.6 and 0.7. So what I am saying here, if you are given the sphericity and the nominal diameter, or you are given the sphericity and the equivalent diameter, then this is equal to the effective diameter. All what you have to do is just replace dp with phi s with the new dp. طبعا it is the same symbol dp in both cases, but you know what is the difference between them now. طبعا we can have different shapes of particles. As you can see, all of those shapes, they are not spherical. So this is why we define such as a nominal, equivalent, and effective diameter. So all of those are different shapes that you might face. So here then I talked about three concepts: a relation between the bed height and the porosity, and we have done that using the volume balance. Then we obtained a relation between the pressure delta P, the pressure in the fluidized bed, and LMF, the height at minimum fluidization, and we got this using the force balance. And finally, I defined for you sphericity or shape factor, and I can use it whenever I have those non-homogeneous, non-spherical particles. And all what you have to do is to replace, let us say, the effective diameter with the sphericity times the nominal or equivalent diameter.